Alright, this is a example of the infinite square well. I'm going to start off with the infinite square well, but I'm going to adjust some of the boundary conditions so that it's more finite, has more finite properties. As you might know, the infinite square well is just a classical example to demonstrate the Schrodinger equation, which is a differential equation. And this differential equation represents something, or it looks similar to the differential equation for a spring. So the solution is going to be, it's going to look somewhat like a cosine or a sine function. So to begin, I'm going to show you just how it works. There's specific values for E in this equation that produce solutions to this infinite square well, because it's basically from the origin 0 and then to some other point on the coordinate system. I'm just going to use 1. So from 0 to 1 it's going to be 0 potential, and everything else will be infinite. So it can't exist outside from 0 to 1. And so basically we're going to find a solution. There's many solutions that can be used, and there's many values of E that can give solutions, but they won't all produce graphs that start and end at 0 and 1. So we're going to look for an actual solution that starts at 0 and it finishes at 1. And to do that, we're going to test every value of E. So E is 0. We're simply going to go through and do a while loop. I'm going to walk you through a little bit, but we're basically just going to draw the graph out with E equal to 0, and then of course it's not going to work. We're going to increment E by a small amount, and then keep trying it until it works. Once the solution starts at 0, or the psi function has a value of 0 at x equals 0, and psi has a value of 0 at x equals 1, it's going to stop and then actually print out that E value. And there's many multiples of E that would work. So let me show you real quick how it runs, how it works. I'm going to go back to explain the code a little bit. And it stops. So it did a whole lot of calculations, and then when it got to a solution that started and ended at the boundary points, it stopped, and then it printed out the E value, which is 4.92, and the actual value of this graph is almost 0. So that's pretty good. And just to explain code a little more, this part right here, just ignore for now. That's not part of the infinite square well. Your typical differential equation, the second derivative first, and the actual function. Just like if you to do anything else, except where most of the other examples we use were time, we just increment x the same fashion. Okay, here's the if statement. This actually stops the loop if the value of psi, in this case, is 0.002, which is almost 0, and that's good enough for us. And that's just going to stop the whole loop. This find variable was once set to true. It makes it false, breaks the loop, and you get we print the value of E and the value of psi. And if this doesn't happen, which it doesn't until the end, it skips over this and it adds a little bit to E, redoes it over and over until it hits this point. It's a true solution. Then we got our case. Let me show you real quickly. It was 4.92 for the value of E, so the next solution would be higher than that. A lot more than 5, so I can start at 5, it will work. And you're going to see more of a sine function. And then if we were to keep doing this, I could add values really high for this particular program, and you'll see it's more of a higher frequency, but it's always going to start and end at these 2 points. So I'm going to put it back to 0, and that was for the infinite square well. This right here, the length was 1, so if it's less than a half, nothing changes, the potential 0. But there's going to be a bump. If it's larger than half the length, then the potential is going to be 3. And it's going to have a bump in this well. It's going to be more finite. So let me just run this program again. At the E is 0, just like we had last time. And before we add the bump, it was a perfect symmetrical hump. But as you see now, it's hard to see exactly, but it's definitely not symmetrical by looking at it. And you can see the value of E was once 4.92, now it's 6.32. So it's with this bump, the solution won't work. We had to find our new solution. And that's how we do it. So what I say, it was 6, so I could do 7 just to see, to find the second solution. And you see it's similar. Last time, well, I didn't do it in this video, but it was 19 point something for the second solution without the bump. Now it's 21.6, so it's a different, you can see it's doing something different. And that pretty much wraps it up. I'll try to do a follow-up video and actually replace this video in the future. I'll replace this video and have a better one up, so I go more in detail about what just happened. But thanks for watching.